So just to kind of remind you of where we are and what we've been doing, okay? Chapter 11 is titled Liquids and Intermolecular Forces. So intermolecular forces have been our dominant topic of late. And last class we started to talk a little bit about how that's involved in phase changes, and now we're going to put some math to phase changes. Okay. Now this is something that is covered in Chem 1. However, most of the Chem 1 teachers here at Oakton at least teach this right at the very end of the year, and it's taught kind of quickly. So I'm going to review this with you in some detail because I want to make sure you understand it. So this is something called a heating curve. Right? Temperature would be on the y-axis, and on the x-axis, I think this is time. It actually doesn't even, the x-axis we don't even care about. It's the y-axis that we care about. And essentially, what I want you to imagine is if you took a sample of ice out of your freezer and just put it out on the counter, what would happen to it? Now, your freezers, you know, in your homes are not kept at 0. Freezers are kept below the freezing point. So when you first take that ice out, it's not at 0. It's maybe at -20. Okay? But as it sits out on the counter, its temperature is going to steadily rise. And what we're going to do, guys, is label this curve with some details to make sure that you know what state of matter is appearing at every single little point. Okay, so obviously this is solid, and that solid is getting warmer, getting warmer, getting warmer, getting warmer, and then we get to 0. What's so magic about 0? What's so special about it? It's the melting point. Okay? At that point, right there, okay, that ice is still 100% solid. Now, what's going on as I cross over here? What's happening? It's melting, 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 all melted. So that point right there, we are 100% liquid. Now what I want you to notice is until that ice is 100% melted, converted to liquid, the temperature will remain absolutely stock still at its melting point. Okay? As long as there is some solid in there, it will be at 0. Okay? Only once we get to 100% liquid can then the temperature start to rise again. All right? And, you know, again, you've just put the ice out on the counter. Your house is probably somewhere around 25 degrees here. But you then take this liquid water, and you don't just leave it out on the counter. Now you put it in a pot on the stove. So now its temperature is rising again. Rising, 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 rising. What state of matter do you think I am at that dot? Liquid. Okay, we're still all liquid right there. And then what's happening as I go across here? Don't use the word boiling. Let's use a better word. Vaporizing. Vaporization. We're vaporizing until it's all what state of matter? Gas. Okay? And only until it is 100% gas can then the temperature start to rise again. Okay? Same thing we had down here. The temperature will stay at the boiling point until it is all gas. So it's important to know what states of matter are where. Let's talk about what math do you use where on these curves. Because let's say I asked you to calculate how much heat is required to convert this chunk of ice out of your freezer at -20. How much heat is required to convert that chunk of ice into a sample of steam at 120 degrees? You're going to have to do calculations at each step. Okay? We're talking about heat. Now, let's look at this first slant right here. Yes or no? Do I have, or let me ask it a different way. From here to here, is the temperature changing? Yes or no? From here to here?
Yes.
Yes. Do you know an equation from long ago that involves heat and a change in temperature? MCAT! You got it. Okay. And that is the exact equation that you would use on this part. Now let's review what MCAT is all about. What is Q? Heat. Do you remember what the units are for heat most of the time? Joules. Okay. What's M? Mass in grams. See? Specific heat capacity. And for this part right here, you have to use a specific heat capacity, the one for ice. And delta T is what? Change in temperature. Okay. Do I have a change in temperature from this point to this point? Yes or no?
Yes.
Yeah. So I would use that equation there as well. My mass would be the same. The specific heat number would be different because this would be for liquid water. Okay. Up here, I can use it again. This time the specific heat would be for that of steam. Do I have a change in temperature here? Yes or no?
No.
No. So I can't use that equation to calculate a heat here. So what do you do? Something else. Here's how I'm going to write it. The heat where melting is occurring is equal to amount of my substance, and I'll tell you in a second why I write amount, times the heat of fusion, which would be given to you in the problem. The reason I say amount is because sometimes what you would plug in there would be a mass in grams. Other times, it would be a number of moles. How do you know? It depends on the units given to you for this. For example, if heat of fusion in the problem is given to you in joules per gram, then plug in a mass in grams. If it's given to you joules per mole, then plug in moles. Okay. Do I have a change in temperature up here? Yes or no? No. So I have to do the same thing. What would be the only difference up here? Instead of heat of fusion, it would be the heat of vaporization, which again would be given to you. Okay. So I'm going to walk you through an example of one of these heat curve questions. Okay. Problem says, calculate the amount of energy in kilojoules needed to heat 346 grams of liquid water from 0 degrees to 182. And then they give us a bunch of other extra information that we will need later on. My suggestion when tackling a problem like this is draw out that stair-step energy curve. Do a quick sketch. Okay, now this is water we're talking about, so what's the temperature at that first line? 0, okay. And this one, 100. Okay. Let's figure out where we are starting and where we are ending. It says that we are starting at 0 degrees, but this whole line is 0 degrees. How do I know where to put a dot for where I am beginning? Okay, it says it's liquid, so where do I put a dot? Left, middle, right?
Right.
Okay, very good. If it said we were starting with ice at 0, then my dot would be in that corner. Okay, but that's where I'm starting. We're going to heat up to 182. Well, that's somewhere above 100. I'm just going to put an X up there. 182 degrees. The beauty of doing this, like drawing this out before you even tackle the problem, is this will tell you how many steps the problem is. It is 1, 2, 3 steps long. Okay? So let's get to it. All right? I'm just going to walk you through this one real quickly. So, step 1, from here to there, what equation should I use to calculate that heat? MCAT. Okay, great. So 346 grams. And we were given more than one specific heat. What specific heat am I looking for? The one in the liquid phase, which you probably have memorized anyway, 4.184. What would be my delta T, ladies and gentlemen, from that point to that point only? 100, not 182. All right, I'll save you the time. You end up getting essentially 145,000 joules. They want our final answer in kilojoules. How many kilojoules is that? 145. Okay. Step 1 done. What do I do to make my calculation for this second step? What's amount times? Okay, amount times the heat of vaporization, H-vape. Okay, well, let me just go back to the problem here. So let's find, here's our heat of vaporization. What do I want for my amount? Moles. Was I given moles of water? No, but I can get it. Okay, I'll save you the time. 346 grams of water is 19.2 moles of water. Okay, moles cancel. I'm already in kilojoules. How nice. Bless you. Okay. Last part. What do I do? MCAT again. Same mass. Different specific heat capacity. This time I want it for H2O in the gaseous phase, which is a different number. They give it to us. And what's the delta T from this point to the X? 82 degrees. do you suppose I do to get the total? Add them up. That's it. I add all my heats in kilojoules. You should get something pretty close to this number. Problem done. Okay? So we teach that in Chem 1 because that's, that's not terribly difficult. It's just which equation do you use at which point. That's all. Are you likely to be given a question like this just by itself? Probably not. Usually what an AP question might have, and I'll show you one in just a second, is maybe not a 3-step, maybe a 2-step heat curve kind of question, but it's part of another question. It's part of a larger question. Like this. I love this question. I love this question because I'm going to tell you how refrigerators work. And you may not know how refrigerators work. And it's fascinating. It's genius. Okay? Let's read it. It says, compounds like CCl2F2 are known as chlorofluorocarbons, CFCs, and were, meaning past tense, used as refrigerants. These are chemicals that used to be used in refrigerators. Why aren't they used anymore? They're dangerous, they're bad, they're harmful to the environment, they kill the ozone layer. Okay? They give us the heat of vaporization for this CFC. And it says, what mass of this substance, meaning the CFC, must be vaporized to freeze 200 grams of water initially at 15 degrees. Well, before we even make a plan of attack here, I want you guys to understand how refrigerators work, and this is fascinating, okay? What's the purpose of a refrigerator or a freezer? To keep things cold, right? Okay, so you had, fried chicken for dinner, okay? And you made too much, so you have leftovers. God, I'd kill for some fried chicken right now. Anyway, but you made too much, you've got leftovers. So your leftovers, because, you've had a lengthy dinner, they're probably about room temperature at this point. Dinner's over. You put them in a thing of Tupperware, and you put the Tupperware in the refrigerator, right? What happens to the temperature of the fried chicken overnight? Drops. If you put it in the freezer, it's going to freeze. The temperature is going to fall. No matter if you put it in the refrigerator or the freezer, doesn't matter. Well, guys, the way refrigerators work, and they don't use CFCs anymore, but they still use chemicals similar to it. They use these liquids that will vaporize. Now think about that for a second. A liquid is vaporizing into a gas. Is that an endo or exothermic process? Endo. Heat is required. Heat must be added to that liquid to get it to vaporize. Where do you think that heat is coming from? From the food. Exactly. Okay? Your refrigerator, and I don't know how it does this, it's magic, okay, pulls heat from that fried chicken that you just put in the refrigerator and uses it to fuel this vaporization process. So the heat is pulled from your fried chicken from dinner and is used to vaporize these refrigerant chemicals. Okay? And if you put something else in the refrigerator that's, at room temperature or warm, or even just opening the door of your refrigerator, okay, is causing the temperature to rise inside your refrigerator, and that's just another source of heat that can be drawn and used to vaporize. Now, here's the other part of your refrigerator that's just sheer genius. You might say, well, don't you need like an endless supply of these liquid refrigerants if we're vaporizing them all the time? If you've ever seen the back of a refrigerator, and I don't know if newer refrigerators do this, but older ones used to have these coils, these like pipes that would run down the back of the refrigerator in like a serpentine kind of way. Your refrigerators also are equipped with compressors. Okay, your car has a compressor on it too. Lots of things have compressors. Once the gas is vaporized, the compressor compresses the gas and converts it back into liquid form, and the process can start all over again. So those refrigerants are just recycled constantly. I think that's really cool, right? But again, my sense of cool is a little skewed. All right, but let's look at this problem and let's come up with a plan. Because we don't have just one thing to worry about, we've got two. All right, but I'm going to start it just like I did the other one. I'm going to draw that heating curve sketch. All right, this is 0. This is 100. Okay? We are starting, let's look at the water first. We are starting with water at 15 degrees. What state of matter is H2O at 15 degrees? Liquid. Okay, so let's put our starting dot like there. Okay. Now what are we doing to it? We're putting it in the refrigerator. What's going to happen to the temperature? It's going to drop. So we're moving this way down the curve, not up this time. And we're not just lowering the temperature, we're also going to freeze it. Where should I put my X for where we're ending? The left side here? You got it. It didn't say that I'm freezing it and cooling it down further. They didn't give us a second temperature, so I assume we're stopping there. This is a two-step process. Do you agree? Okay. Am I taking heat away or adding heat to this water if I'm cooling it down? I'm taking heat away. And where is that heat going exactly? It's being used to do what? It's being used to vaporize the CFC. So I'm going to let you do this problem on your own, but first thing I would do is calculate how much heat is being removed, how much heat is lost from the water. And here's the big overarching thing that's going to help you solve this problem. However much heat is lost by the water will be equal to the heat gained by the CFC. Okay, let me say that one more time. Calculate this first. Figure out how much heat this even is, these two pieces together. The heat lost by the water will be equal to the heat required, gained to vaporize the CFC. Okay, see if you can figure it out. I think you can. Okay, check what you've got. Tried to make this as clear as possible. Please ask questions if something is unclear. So the reason that the part for the CFC is so short is because all we are doing to the CFC is vaporizing it. We're not changing its temperature at all. I didn't have to draw the stair-step curve for this one. all I was doing was vaporizing it. And if you're vaporizing something, this is the equation that you need to think about. But I was missing a piece. Set them equal, and you can solve for that question mark. Somebody this morning asked, why aren't these two heats negative? Because you are cooling it down. If you wish, you could bring in that negative. I mean, if you're going to be very strict about, delta T is always final minus initial, which you can do that, then yes, you will get a negative number right here. But you also need to make this one negative as well, because freezing something is an exothermic process. These both are negative, then that means this one is negative. And when you come to here, you would say the same thing, but you would say heat lost by water is equal but opposite in sign to the heat gained by the CFC. Do you remember that back from thermochem? Okay. It's your choice. You can keep everything positive or you can incorporate that negative. It's up to you. You'll get the same answer. And ladies and gentlemen, that is the end of chapter 11. Chapter 12, guys, is all about solids. Okay, and we're going to have some real world application in here, just like we did the last chapter. Okay, now, there's basically two types of solids in this world. Here's the first type. Can you tell me, this is good like SAT prep, if you have the letter A or an at the beginning of a word, what does that mean? Not, okay? The word form morph, okay? Don't think like, what does it mean in English to morph? That means like to change. Do you know what the word form morph refers to? Yeah, shape. Without shape. Amorphous solids are one type. Meaning if you were to look under a very powerful microscope and see what do those solids look like on an atomic molecular level, you would see no organization. Just a mishmash of atoms and molecules. No pattern, no nothing. Glass is an example of an amorphous solid. No structure to it. Most solids, however, guys, do have structure, and those are called crystalline solids. They have some sort of structure, some sort of repeating pattern to how they are put together, like something like that. Okay, we've seen that word before, lattice. Right? We saw it when we talked about lattice energy, but the word lattice just means organized structure, a lattice structure. Now, crystalline solids, they don't have to be organized exactly like this. It doesn't have to be a cube on top of a cube on top of a cube. You know, this is my molecular model for ice. Does this look like it has structure to you? Yeah, it does. They're not cubes, but it is structure. Okay, or we're gonna look at models today. Or like this one, for example. Does that have order to it?
Yes.
Yeah. Again, it's not cubes, but it does have a regular repeating pattern. That's all it means to be a crystalline solid. Now, part of what you will be asked to do in this chapter is to classify solids. You'll be given some substance and it'll say, what type of solid is this? If we're looking at a crystalline solid, which you will be, there's 4 types. Here's the first. First type of a crystalline solid is an ionic solid. Okay? Guys, how do you know? Think Chem 1. How do you know if a compound is ionic? Metal and non-metal. Okay. These are things that have structure. I am no artist. Forgive my lack of drawing ability. I'm attempting to draw something three-dimensional here. It's not bad. Not bad. Now, a lattice structure, again, doesn't have to be a cube, but that's the easiest thing for me to draw. This term, lattice point, okay, it means at the junctions within that lattice structure. In that drawing, it happens to be the corners, but if I were talking about this guy, the lattice points would be anywhere that you see a black piece. Okay, it's just wherever in your lattice structure are the junctions. Those are called lattice points. If we're talking about an ionic solid, what's at those points are individual ions. So if we're talking sodium chloride, a sodium ion would be at this point. What do you think would be at the point next to it? Cl minus. You're right. Why not another sodium ion? Yeah, same charges repel. We want to have opposite charges next to each other. So what would be at this lattice point? Cl minus. Okay. This would be Na plus, Na plus, Cl minus, and so on. Okay. Now, there was a fancy term. I introduced this to you early on in the year. Opposites attract. There's a fancy term for that. Electrostatic attraction. Ladies and gentlemen, if you are ever asked what holds an ionic solid together, don't say opposites attract. Be fancy. You say electrostatic attraction. That's what holds an ionic solid together. Okay, if it's still a compound, but it's not ionic, it must be covalent, and that's our second type of solid. Let me give you a little clue, ladies and gentlemen. If you see the word molecular ever, anywhere, that is code for covalent. We don't ever use the word molecule or molecular if we're talking about something ionic. This is a word used in covalent situations. So a covalent solid. Okay? Covalent solids, molecular solids can still have structure. They can still have a lattice structure. But we're not going to have ions at the lattice points. There are no ions. What are we going to have? We are going to have, let's say it's ice. We're going to have the entire molecule at each lattice point. Okay, no ions. We'll have the entire molecule. Now, in the previous drawing, what was holding one ion to the other? What was the fancy term? Electrostatic attraction. What's holding these things together? What is attracting one water molecule to another water molecule? Think last chapter. Intermolecular forces. Yeah. What holds a molecular solid together is intermolecular forces. Okay? So we've got one type of crystalline solid, a second type, here's a third type. Maybe it's a metallic solid. Okay? I mean, think about it for a second, guys. If you have a bar of gold, oh, if only. Okay, gold, pure gold. Is that ionic? This is not a trick question. No. Is it covalent? No. Gold isn't a compound at all. It's just a pure element. It's a metal. Okay? Now, we have seen this word before. We saw this word when we talked about resonance. We're not talking about resonance here. Do you remember what this word means? We talked about it with pi bonds, but this doesn't necessarily mean pi bond. Can move around. That's all delocalized means, is can move around. Metals contain delocalized electrons, electrons that can move wherever they want. Sometimes you'll see it described as metals have a sea of electrons. Electrons can just flow like water through a bar of gold, which is why they are such excellent conductors of both heat and electricity. Electricity is nothing more than flowing electrons. That's all it is. Okay? So if you're given a metal, it's a metallic solid. Your fourth type is called a covalent network solid. Sometimes you can drop that word covalent and just say a network solid. Your textbook goes into great detail about how network solids are held together. Guys, all I want you to focus on is the fact that they are held very tightly together. Extremely strong bonds. And I want you to know these examples. Carbon, diamond, and graphite. And we're going to talk about these two in more detail in just a second. The element silicon. A lot of your computer parts are made of this. Silicon dioxide is another network solid. Does anybody know the more common name? Okay, sand, true, but sand is really just ground up what? Quartz. Okay? They also make glass out of this. Okay? But these are network solids. All I want you to really focus on is that their bonds are crazy strong. Okay? And we're going to focus in on carbon here for a moment, because carbon is very bizarre. I say it is bizarre, guys, because most elements, when you find them in nature, they exist in just one form. Carbon exists in 3 forms. This word allotrope just means form. The most common form of carbon is coal, okay? Like charcoal. And coal, ladies and gentlemen, is an amorphous solid. What does this word mean again? No shape, no organization, no structure. And I say boring because there's nothing to talk about. Okay, so we're moving on. Coal is one form of carbon. Here's the other, okay, or an other. Diamond. Okay. This molecular model that I have right here, this is diamond right here. Okay, as you may or may not be aware, I hope you are, diamond is the hardest natural substance on Earth. Okay, and diamond was an example of what type of solid, just from the previous slide? A network solid. Extremely strong bonds. Okay, and let me jump ahead here. Okay, there's a picture of it there. I'm also going to walk around with this model here, and I'm sorry if you can't see. It is sort of hard to see. What I want you to do, as best you can from wherever you're sitting, focus your eyes on just one of these black carbon atoms, particularly one that's more towards the center of the model. Don't look at one towards the edge. What shape do you see around that carbon? Tetrahedral. Yeah. Diamond, okay, solid diamond is carbons that are tetrahedrally bonded to each other. They have sp3 hybridization. These are all sigma bonds, very strong. Okay, so this is what diamond looks like. And something else to know about diamond. All right, let's talk about its conductivity or lack thereof. What did I say electricity is? Electricity is flowing electrons. I want you just to look at this model. I mean, this is a really tightly packed solid. Does it look like there's a lot of room for things to move around in there? No. And ladies and gentlemen, if electrons cannot move around, flow, whatever, then they can't conduct electricity. Diamond is a very poor conductor. What's the opposite of conductor? Insulator. Diamonds are excellent insulators. Okay, if we had unlimited resources, we should make all of our travel coffee mugs out of diamond. We should build all of our homes out of diamond. I mean, despite the fact that you're living in a see-through house, whatever. Doesn't matter. Okay? But because these electrons there's no room for them to move around, diamonds are excellent insulators. I'll pass this around. We're hands-on today. Let's talk about the third allotrope of carbon, graphite. What's in your pencils? It's not lead, ladies and gentlemen, even though we often say that. Okay. This is graphite. Looks quite different, doesn't it? All right, I'm going to turn this on its side so you can see this a little better. Look at each carbon atom again. What shape do you see? Trigonal planar. Trigonal planar. What's the bond angle? 120. Okay. Graphite, ladies and gentlemen, has these 6 carbon rings bonded together with a trigonal planar shape. Planar means what? Flat. You get these layers with graphite. Okay? You get sp2 hybridization. Now, in this model here, the green connectors represent sigma bonds, very strong. These white pieces represent pi bonds, which are not as strong. And guys, this is what is so cool about chemistry, is that structure defines function. Okay? If you get your hands on some powdered graphite, and I have some if you want to try it at the end of class. Powdered graphite is a bizarre substance. It's a solid, but when you get it on your hands, it's very slippery. Now, it's weird to describe a solid as being slippery, but if you rub it on your hands and rub your hands together, it almost feels like your hands are wet. But they're not, okay? But it feels that way. And if you want to try it at the end of class, we can. Locksmiths. Hopefully you don't ever have to call a locksmith, because that usually means you're locked out of your house or something. They use powdered graphite as a lubricant in locks, because you don't want to put something like oil, which is really slippery, into a lock, because you don't want a liquid in a lock. I mean, then the lock can rust and the whole thing. So they use this powdered graphite. And the reason that it's slippery is because because these pi bonds are kind of weak, these layers literally slide past one another. I think that's just fascinating. Okay, so I'm gonna pass this around. This is graphite. Very different. That's what it would look like if you could look at it under a microscope. Okay. And if you guys just look at these two models where they are. Look at diamond right here compared to graphite. Does graphite look like there is room for electrons to move around? Yes. Graphite will conduct electricity. So please, not that you would, because you guys are smarter than this, do not take the sticks of graphite out of your mechanical pencil and put them into the electrical socket, because it will conduct and it will light you up like a Christmas tree. Don't do it. Not that you would. Not that you would ever do that. No, no, no. Okay? But, guys, the point is, the way things are connected dictates how they behave. Okay? Carbon, diamond, and carbon graphite are exceptionally different because of the way they are held together. Okay? Now, I said that there are 4 types of crystalline solids: ionic, molecular, metallic, network. Of those 4, the one that you're going to be asked about the most often are the molecular solids. So I just want to focus on those for just a minute, and we're actually almost done here. Okay? You see the word molecular, what does your brain think? Covalent. Covalent compounds, what does it mean without a dipole? What does that mean? Non-polar. We're talking non-polar covalent compounds. Okay, now let's review. If something is non-polar, what intermolecular forces does it have only?
London dispersion.
London dispersion. Are those relatively strong or weak? Weak. Okay. So the point is, most non-polar covalent compounds at room temperature, ladies and gentlemen, are gases. Why? Because they are held so loosely together. It's like the heat of a room at room temperature is like too much for it. It can't handle it. Okay? The heat, the bonds between the molecules in a non-polar covalent solid are so weak that they easily melt and easily boil, so most of them are gases. I don't know if I have ever pointed this out to you, but I love being in this room because I have the best periodic table of all the chemistry rooms. I don't care what they all say, I have the best one. The reason I say that is because mine is color-coded. If you'll notice, most of the element symbols are colored gray, and that means most of the elements are solid at room temperature. You'll notice there's only 2 elements that are colored blue. Those are the only 2 liquids at room temperature. The ones mostly in the upper right-hand corner that are colored sort of orange, those are gases at room temperature. Okay? Now, why am I pointing that out? Well, I'm going to ask us to compare some molecules here. Fluorine, chlorine, bromine, iodine. Okay. If you have 2 fluorine atoms bonded together, well, this whole bundle, this F2, do you all agree that that will be nonpolar? Do you agree? All of these are nonpolar. Which means all of them have what intermolecular force? Only. Okay, great. All of these are held together very weakly. But look at our periodic table. Fluorine and chlorine are gases at room temperature. Bromine is a liquid, and iodine is a solid. Let me translate that a little bit here. That means fluorine and chlorine are held together pretty loosely. Bromine is held together a little bit more tightly, and iodine is held together the tightest of all. Why? I mean, they only have LDFs. I thought these were supposed to be super duper weak. What's going on with iodine here? That's that $1 million word. I2 is a very polarizable molecule. And why is that? Because it's so large. Okay? Compared to fluorine, iodine is much greater in size. It has a much greater molar mass. It has a much greater number of electrons. It's very polarizable. Which means, yes, it has LDFs only, but its LDFs are a little stronger than this guy's LDFs. Strong enough that he's solid at room temperature where he is a gas. Okay? Polarizability. Please don't forget that word. That is a word you use when you're comparing things that have LDFs only. Okay? When you're comparing molecules that have LDFs only, you have to start looking at atomic size and think about that word polarizability. Okay? Because this is so polarizable, it can be a solid at room temperature, even though it has LDFs only. Okay? If we're talking covalence without dipoles, meaning nonpolar, the other type would be, what if they are polar? And guys, if a molecule is polar, it doesn't have just LDFs. What else does it have? Dipole, and it might also have, hydrogen bonding. Okay? But guys, there is something that I want you to be aware of. Let's talk about the strength of these forces. Which LDF, dipole, hydrogen, which is the weakest of those three? Okay, LDF. Next in order would be dipole. Hydrogen bonding is our strongest. But ladies and gentlemen, I want you to understand, even hydrogen bonding, that is the strongest intermolecular force, is not even close, not even in the ballpark, to the strength of an intra-force. What are the two types of intra-forces? Ionic and covalent. Okay, so here's the order here, but this isn't even close to the strength of an intramolecular force. Which one is weaker, covalent or ionic? Covalent. So here's how I'm going to illustrate not in the ballpark. Okay, covalent bonding. And then this isn't even close to the strength of ionic bonding, which is significantly stronger. So what do you think is going to have the highest melting points? You know how I can prove it to you? Have you ever seen liquid table salt. I don't mean salt water. I mean liquid, molten NaCl. Have you ever seen it? Me neither. Do you know why? It has an incredibly high melting point. I looked it up. It's 800, right around 800 degrees Celsius. Our ovens don't go to 800 degrees Celsius. All right? Do you know what would have an even higher melting point than this? We got an example, one of our models here. Diamond. Okay? Diamond would be even higher than that. Okay? And we've already talked about this. Here is your last task, ladies and gentlemen. And if you finish it, then you can play with the powdered graphite if you like. Here's what I am asking you to do. For each element or compound, I want you to tell me what type of crystalline solid it is. Remember the 4 choices. Ionic. What is the second one? Molecular. What's the third? Metallic. Network. Okay. Tell me which type it is. And there's a follow-up. There's a second part. If it's a molecular solid, I want you to tell me what intermolecular forces are holding it together. Check them, please. Check your answers. Do you guys know what I mean by all three? All 3 types of intermolecular forces? How come this last one down here, how come it doesn't have hydrogen bonding? It has hydrogen. It doesn't have N, O, or F in it. You got it. And that's it for chapter 12, by the way.